Hello everyone, welcome to the second video lesson for Chapter 2 of Foundations of Scalable Systems. In the previous lesson, I described the advantages of scaling out services across multiple service replicas to increase a system's capacity. Scale out is a highly effective strategy. But like, well, basically any great idea, there's a downside. Reality always arrives. As you add new service instances, the system's capacity grows, potentially infinitely. At some stage, however, reality bites, and the capability of your single database to provide low latency query responses will diminish. Slow queries will mean longer response times for clients. If requests keep arriving faster than they're processed, some system components will eventually become overloaded and fail due to resource exhaustion. This is not good. Essentially, your database has become a bottleneck that you must engineer away in order to scale your application further. Scaling up is an effective strategy, just like with services, for scaling our databases. We can increase the number of CPUs, the memory, and the disks available in our database server, and this can go a long way to scaling our system. For example, at the time of writing the book on Google Cloud Platform, you can provision a SQL database which has 96 virtual CPUs, 624 gigabytes of memory, and 30 terabytes of disk, and can support 4,000 concurrent connections. This will cost you somewhere between $6,000 and $16,000 US a year, which doesn't sound too bad a deal to me. Scaling up is a very common database scalability strategy. As your databases grow, they need constant care and attention to keep them tuned and running fast on the hardware. There's a lot of wizardry in this job, such as query tuning, disk partitioning, indexing, on-node caching, and hence database administrators are really valuable people that you want to be very nice to. They can really make your application services highly responsive. In conjunction with vertical scaling, another highly effective approach is to query your database as infrequently as possible from your services. We can do this by employing caching in a scaled out service tier. Caching stores recently retrieved and commonly accessed database results in memory so that the results can be quickly retrieved without placing a burden on the database. For example, the food menu for a restaurant might change daily, but may be queried hundreds or thousands of times a day. You can use a cache to store the menu once it's issued. All the client requests will then read from the cache until the actual menu changes. For data that is frequently read and changes rarely, your processing logic can be modified to first check a distributed cache, such as a Redis or memcached store. These cache technologies are essentially fast distributed key value stores with a very simple API. This scheme is illustrated on the slide here. Note now that the session store from the previous lesson has disappeared. This is because you can use a general purpose distributed cache to store session identifiers and content along with application data. A well-designed caching scheme is invaluable in scaling a system. Caching works great for data that rarely changes, such as inventory catalogs, event information, contact data. If you can handle a large percentage, maybe 80 or 90% or more of read requests from your cache, then you effectively buy extra capacity at your database, as they never see a large proportion of the user requests. Still, many systems grow to need to access terabytes or more of data rapidly, and this makes a single database effectively prohibitive. In these systems, you need a distributed database. This slide shows how our architecture incorporates a distributed database. As the data volumes grow, a distributed database has features to enable the number of storage and processing nodes to be increased. As nodes are added, the data managed across all the nodes is rebalanced to attempt to ensure the processing and storage capacity of each node is equally utilized. Distributed databases also promote availability. They support replicating each data storage node so that if one fails or cannot be accessed due to a network problem, another copy of the data is available. The models utilized for replication and the trade-offs these require, spoiler, consistency, are covered in later lessons. Distributed databases is a complex area, and it's one I'll cover extensively in later lessons. In very general terms, though, there's two major categories. First, there's distributed SQL stores from a whole range of vendors, traditional ones like Oracle and IBM, and newer vendors such as Google. These enable organizations to scale out their SQL databases relatively seamlessly by storing the data across multiple disks that are queried by multiple database engine replicas. These multiple engines logically appear to the application as a single database and hence minimize code changes. Secondly, there's distributed so-called NoSQL data stores from another range of vendors. These products use a variety of data models and query languages to distribute data across multiple nodes running the database engine, each with their own locally attached storage. For large-scale systems, scaling the data tier is one of the greatest challenges in system design. Many of the issues are covered extensively in Part 3 of the Foundations of Scalable Systems. In the final lesson for this chapter, I'm going to talk about how we scale out a system using multiple processing tiers. Thanks for watching.